Welcome to an explanation of prime factorization and factor pairs. The directions here ask us to write each number as a product of prime numbers. Another word for that is to find the prime factorization of a number, and we often use factor trees in order to do that. So what we want to do is we want to find two numbers that multiply to equal this number, 240. If you don't know big numbers that would do that, we see that it is even, so of course 2 is a factor, and 2 times 120 would give me 240. 2 is a prime number, so let's circle it, and we now want to work with 120. Two numbers that would equal 120 are 2 times 60, because again it's prime, and we can keep going. 2 times 30, 2 times 15, and then two numbers that equal 15 are 3 and 5, which are also prime. So if we want to write 240 as a product of prime numbers, we would multiply it 2 times 2 times 2 times 2 times 3 times 5. Or we could write that using exponent notation as 2 to the 4th times 3 times 5. Now let's look at the same example, but using different factors. So maybe you notice that 240 could also be written as 24 times 10, because it ends in a 0. And then 24 we know is 4 times 6. 4 we know is 2 times 2. Now we finally have some prime numbers here. 6 is 2 times 3, which are also prime numbers. And 10 is 2 times 5, which are both prime numbers. So here we have 4 2's, a 3, and a 5, just in a different order. So if we reorder them, we end up having the same exact final answer as we did before. So this just goes to show that it doesn't matter which two numbers you pick. When you start your factor tree, you'll end up with the same prime numbers at the end. Now this next example I put because it's not as obvious to see what would easily divide into 231. Well, if we remember our divisibility rules from the previous section, we can add the digits together, 2 plus 3 plus 1, and we get 6. So we know that this number, 231, is divisible by 3. So I'm going to go over to the side here and show my division, which you may need to do. And if we divide this using long division, 3 goes into 23 7 times, which is 21, and 2 left over. Bring down the 1. 3 goes into 21 7 times, which is 21. Of course, we should have a remainder of 0 because we know it divides evenly. So that tells me that 231 is 3 and 77, and we know 3 is prime. Now 77 we get by multiplying 7 and 11, and those are also both prime. So here's an example where we just have 3 times 7 times 11, and no prime factor is repeated. This last example I put because all of the divisibility rules that we know for those basic prime numbers do not work for this. It's not even. If we add the digits together, we end up getting 11, which is not divisible by 3 or 9. And so then we have to look at other values. So we think perhaps 7. 7 is a prime number. We don't have a divisibility rule for it, so let's try and see what happens when we divide by 7. 7 goes into 11 one time, and if we subtract that, we end up getting 4. Bring down the 9, and 7 does go into 49 evenly 7 times. So we do have a remainder of 0. So that means that 7 times 17 equals 119, and those are both prime numbers. So our final answer here is 7 times 17. Now I wanted to put this example just to show you that sometimes the prime numbers are not the small, commonly used prime numbers that we see. So you may need to just trial and error some other ones. The next section is going to talk about factor pairs. The directions here say to find pairs, so we need two numbers, that are integer factors of the given number. Now in this case, they do not have to be prime. So what are two things that multiply to equal 12? Well, the most obvious would be 1 and 12, right? Every number you can get by multiplying it by 1. Then what else will multiply to equal 12? Well, we have 2 times 6. What else will multiply to give 12? 3 and 4. And it ends up that those are the only 3 pairs of integer factors that are positive that'll multiply to equal 12. Well, what is a nice way that we can do this with an order? Well, what we can do is we can always start with 1, and we can go up from there, try 2, try 3, and keep on going until we exhaust all of the possible integers. So with this example, 42, we know that 1 divides evenly, 1 and 42. It's even, so 2 divides evenly, 2 and 21. We add the digits together, we get 6, so it's divisible by 3. 3 and, well, if you don't know what that would be, you can always go over to the side and do long division. And get 14. Now 4 is not a factor because 42 does not divide by 4, so we skip it. 5 is not. 6 is. We know 42 is when we get 6 times 7. And here's where we can stop, because if we were to try 7, we already have it here. So once you get values that are already given on the right column here, we know we're done. So these are the only 4 pairs of values that would multiply to give 42.